So by way of introduction,
Thanks, Adrian.
today Dr. Thomas Smolka will be talking to us about the voltage regulating distribution transformers and how they can be used for greater rooftop solar PV integration. Dr. Smolka has been Managing Director of Reinhausen Australia since June 2016, and he was managing the business development of voltage regulating distribution transformers, or VRDTs, at MR since 2012. Previous to his career at MR, Thomas has worked for a DNSP in asset management and innovation. Thomas has a Masters of Science and a PhD in electrical engineering from RWTH Aachen University in Germany. He's a specialist in on-load tap changes, asset management, network planning, power quality, and distributed energy resources grid integration. Thomas is an active member of Seagrey Australia's A2 and C6 panels, as well as the Electrical Engineering Society of Australia. So without any further ado, Thomas, I will hand over to yourself, make you the presenter, and allow you to take us through this topic today.
Yeah, perfect. Thanks, Adrian.
Are you able to present now?
Yeah, no, it's coming up.
No worries.
Perfect. Yeah. Thanks. Cheers.
Alrighty, I'll go on mute and you won't hear from me till the end. Thank you very much, Thomas.
Yeah. Thanks, Adrian, for setting this up. Yeah, ladies and gentlemen, thanks for your time and interest in today's presentation about VRDTs. What does VRDT stands for? Voltage Regulated Distribution Transformers. So I'd like to present a little bit of some history,
Hey,
how
Thomas.
this topic started in Germany. Yep.
Just waiting for your slides to come up at the moment.
Okay.
There we go. Alrighty, I can see your slides now. Take it away. Thanks, mate.
Yeah. Perfect. Cheers. Well, so hopefully that was the last interruption we had from the technical side today. Yeah, once again, yeah, I'm Thomas. Good day to Australia and also overseas. As I saw in the chat, there might be also some guys from Germany standing up, trying to inform more colleagues from me to join the presentation. So hello to you guys, and servus and guten Morgen. So we'll I'll turn my camera off now, so just to avoid any further technical difficulties. So Adrian, let me know if there's anything with the slide, and just start with the presentation now.
Will do. Thanks, Thomas.
So the first slide, I just checked the IEA website again last night. Okay, where are we with the rollout of renewables in Australia? And what you can see here is just an overview of all countries who have, I think, joined the game so far. And there are 4 different phases, so where people trying, or especially network operators, getting issues with DR integration. So we can see here that Australia is right at the beginning of phase 2, minor to moderate impact on system operations. So roughly 10% of electricity is produced in renewable generation units. Doesn't matter if wind, solar, of course, as maybe main part of that, and also other sources. So you can see here what's also interesting. Germany is still quite up, having a share of already 25%. as part of the electricity system, but the two leaders are also coming from Europe, which are Ireland and Denmark, of course, using more wind than solar power. But just to give an overview about, okay, where we are and where we are also in Australia at the moment. Another interesting graph I just found, just also to compare a little bit. I will do some comparison between Australia and Germany, where I'm coming from and where this topic also kicked off a couple of years ago. So you can see here we had, I think, two tipping points in Australia, end of 2010. There wasn't much installed yet, and steady growth over the last 7-8 years, and then here another tipping point where, of course, this kind of battle and run started with integrating more solar farms and wind farms all over the place. Where also, of course, we all can see and notice and listen to complaints and voltage issues on all, I think, voltage levels in the network. So overall, here's also an overview on the monthly PV output in megawatt or terawatt hours overall. So of course, it's depending on the sun. Summer months are better than winter months, but yeah, it's still on a scale where it should be manageable for integration and automation and control in the networks. So what we can see happen, and this is just a screenshot of a power quality measurement I'm running at the moment at my home in south of Sydney. So you can see here the voltages just around lunchtime between 12 and 1 p.m. Yeah, we nearly touched the 253 volts here in south of Sydney. But more interesting also, you can see here there's some swell events, so where the voltage was higher than 253 volts, and all of these 4 cases have happened actually yesterday. So quite interesting to see that, especially in the LV. So this is the behind the meter measurement. We see and notice voltage issues already. So I'm not sure if there's somebody from Ausgrid in the room. Probably we have to discuss this later on, or maybe I have to follow up with them then after the meeting. So how does this topic of voltage regulated distribution transformer start? So as at AMA in, let's say, 2008, I think that was the time when we were working on the first prototypes, and actually customers were knocking and our factory doors and talking to us. So AMA, you can definitely manufacture tap changers for power transformers. So we need a similar thing that we can just put into our distribution transformers. Of course, it should cost nearly nothing, last forever, and be very compact that the transformer doesn't extend its size. Yeah, so we did a little bit of homework. And especially, I think, in the PV gold rush time, so these 6 years from 2009 to 2014, more or less, where we had an installation of more than 30 gigawatts in 6 years in photovoltaics. So that was a big challenge, and more or less 2012. That was the time when I joined, and also we have started to sell and market some solutions and products. But as you can see, of course, some customers had to do BAU, so business as usual grid augmentation, to solve any ongoing LV and MV voltage issues in the network. So here you can see actually our first trial with Energy. That's a regional distribution network operator in Bavaria. probably comparable to Ergon in Australia. And all these red bubbles that you can see were photovoltaic installations, but also we had some biogas, combined heat power systems, also some longer feeders to some farmers as well. So that was a very interesting trial we started, I think, roughly 2008, 2009. So how does the integration of DER lead to voltage issues in the network? So what you can see here is just an overview coming here on the left side from the high voltage substation, looking downwards to the power plug of each customer in the household. In Germany, the voltage standard is plus minus 10%, so network operators are able to plan and operate their network within these limits. And of course, as I hope most of you know, of course, the integration of DER, doesn't matter if it's on the medium voltage or the low voltage or also on the high voltage, will increase the voltage. And then, of course, it can happen that the voltage goes above this 10%, of course, and then we are running the network out of specification. And of course, customers may complain because they got disconnected. Household appliances die or whatever. Yeah, so that's the generation side of it, the blue marks here, but also, of course, looking on the other case, which I think is now nearly 10 years after, a little bit more visible already, is of course electric cars are coming, and then of course, so if there's a high demand for electricity, also the voltage can go downwards and also go to the bottom level of the standard, minus 10% in Germany. So that's also another important thing to know, because if there is a solution within the transformer that can regulate the voltage, it has to cover the voltage regulation in both directions. Yeah, so plus minus, that was a challenge we had to deal with. This slide gives just an overview of course, possible solutions that network operators can use. The first one I mentioned already, curtailment, is something, of course, that is happening quite regularly here in Australia for many customers. And also, of course, looking on the grid codes, reactive power usage or manipulation here as ancillary services is also defined in the different grid codes from all network operators, trying to help them to regulate the voltage or use the reactive power to regulate the voltage. Yeah, so I will come back to that in some more details later on, but just as a summary, what available options we can find. Of course, batteries are also technically possible to regulate voltage in the network as well. If this would be the only use case for batteries, I think that's probably would be the end of it, because they're too expensive to do so. So there must be other use cases as well to make batteries economically feasible. And of course, last but not least, direct voltage control via the VIDTs. So if you compare different voltage standards all around the world, it's quite different. So the WA standard, for example, plus minus 6% is still in place. Yeah, I think there have been a lot of discussion, and Western Power is looking, I think, for extending this voltage bandwidth as well. So Sherwin will maybe talk about this a bit later on. Queensland has recently changed its standard. It's not new anymore, plus 10, minus 6%. Yeah, so which helps them a lot. And the upper limit here, 253 volts, of course, is still in place. And New Zealand, the allowed bandwidth is even smaller, comparable with WA. So if network operators have to to investigate what kind of technical solutions are available on the market to help them with voltage regulation issues. Of course, they have to go back, look in their standards, and then try to find out, okay, what kind of solution may I use for my solution. So looking into the voltage regulated distribution transformer, I think most of you might know that there are two different types of transformers. Standard DT stands for distribution transformer. Most of them have an off-circuit tap changer inside, so you're just going to allow to operate this if the transformer is disconnected. And the VIDT means, of course, just illustrated here with this bike and chain. Of course, that you're more flexible and allow to adjust the settings and add or subtract different windings to the transformers, and by doing so also change the ratio of a transformer and regulate the voltage for all connected customers. So that's a tap changer. This is what our MR manufactures since 100 years, so we have a lot of experience with that. You need just a standard transformer, maybe a little bit more space on top of the cores, and then another voltage regulator relay that can be connected, which has, of course, to do the voltage measurement, and then trigger the tap changer to move to the right direction where it has to be, just to suit the voltage needs in this particular substation or feeders along the line. So here another picture. In the last years, we have worked a lot on different solutions. We have a small toolbox of different kind of tap changers that can be integrated in distribution transformers, also a single-phase unit, which you can see here, which is also has been installed some weeks ago in South Australia. So we're happy to support Australian customers with these kind of solutions, or the three-phase for larger distribution transformers. But overall, I think in a nutshell, it's quite important that OLTCs can be customized in any kind of transformers. So there are different use cases or applications that can be designed to regulate voltage. So I just mentioned below here 2-3 examples: single phase SWR applications, three-phase MV-LV distribution transformer, or an MV-MV regulator, or also, as you will see from another trial or rollout that is going on in Victoria with PowerCore as part of their RevCal project. They have also used a tap changer for regulating of isolation transformers they're using there. Another use case, actually, that is not really common in Germany, I think, nor in Australia, but more in the US and UK. I was just made aware some weeks ago that there is a network operator called Electricity Northwest. So they've done a couple of trials over the last 4 years, sent their submission to the local regulator with this, which is Ofgem, and now finally rolling out this kind of technology, especially for the use case of conservation voltage reduction. So to overall reduce the voltage as much as possible to reduce network losses, but also the use of electricity for all customers, which can save finally some money as well. So that's another interesting use case to think about when talking about voltage regulated distribution transformers. So you all do remember the picture I've shown you 5 minutes ago. So the voltage regulated distribution transformer in the MV-LV use case that we can see here can then of course tap down, tap up to keep the voltage here and the low voltage network stable and between the upper and lower threshold to keep the voltage in line, and allow also by doing this to integrate more DER in Australian networks. Yeah, so talking about use cases, of course, that's quite an interesting question because if you think about regulated distribution transformers, so why have we not installed them in all networks already? So that's just a historical reason, because in the and maybe since electricity was invented and tap changer principles were invented in the 20th century, around 1920, for example. So it was only necessary to regulate the high voltage and the medium voltage. LV, so everything on fixed step could be operated for many, many years. But now with more and more reverse power flow coming up also from the LV, and this is mainly solar roof PV installations, of course, the reverse power flow from LV networks upwards in the upper voltage levels is happening, and now of course such a solution is necessary. So with a VIDT you can easily regulate, like here in the middle use case, completely this blue colored LV regulation bandwidth. Of course then you can also increase the number of solar roof installations in LV feeders. The third use case there on the right is illustrating a bit, okay, what can you do if, of course, photovoltaics are on every household in all streets of rural towns and cities, of course. And then, of course, the opportunity can come up quickly, of course. Why not installing VIDTs in some regions in all distribution transformers, regulating the MV and LV, because then what you can see here is you can also significantly increase the regulation bandwidth on the MV feeders, because you have a solution that can also deliver electricity accurate to the current local standards in the LV, and this would of course give the network operator as much as capacity voltage-wise to integrate more and more renewables and especially solar into the network. So that's an interesting one. So we have actually some guys and network operators in Europe thinking in this direction and rolling out the VIDTs as a standard already on the way, not buying unregulated distribution transformers anymore. So on this slide, you see a little bit what I described with words already. Yeah. So if we compare Europe and Australia, different voltage levels, regulated transformers, which are this icon here on the high voltage, medium voltage side in both countries for many, many years. In Australia, you have, due to the size of the country and rural towns, of course, more long line feeders. That's why also we can see a lot of MV voltage regulators installed in Australia that are supplied by US manufacturers. So that's quite common in Australia. And also on the LV, sometimes buck or boost transformers in Europe or Germany, you would call them farmer transformers, because this might be just a fixed step small transformer on a pole that is pushing the voltage up, that at the end of the line and the long feeder, there's still some electricity and an accurate voltage coming out to connect and supply electricity to this customer. Yeah, so that's what it was before the ER rollout started. So with voltage regulated distribution transformers or tap changers in general, of course, now the level of voltage level MV, LV transformers can be regulated. Yeah, so that's a big step forward in taking care about the voltage from an asset that is also owned and can be controlled by the network operator. Yeah, so we have seen a large debate and discussion, of course, also about network operators trying to control DR and inverters in Europe. Some like that, some are doing this. Others say, okay, it's not my asset, so probably not the best idea to take care about this, but of course define in the grid code how these DR units shall, of course, comply and also offer ancillary services and reactive power flow into the network. So not only deliver active power, also reactive power to help me with my reactive power balance or also some upcoming voltage issues. So the VRDT technologies and tap changers can also replace MV regulators now. So we have seen that. We'll talk about some trials here in Australia as well in a few minutes. And on the LV, I think in some areas, some network operator have already tried some smaller LV power electronic based regulators. Statcoms, for example, 5 kVAR, or similar, just to boost the voltage with reactive current that is generated in these statcoms. So all of you might think, great idea. So why shouldn't we just roll out the VRDT technology everywhere? Of course, everything comes with a cost. And here I've tried to make a quick comparison, of course, or guess about, let's say, customers for network operator or costs for network operators buying distribution transformers, unregulated or regulated, in Australia with an included tap changer or not. Yeah, so this is just an assumption. Don't take me for granted if you get an offer from your local transformer manufacturer. But of course, the tap changer overall, and we have developed one that is maintenance free and will last as long as the transformer lasts, or even longer. So no maintenance over the lifetime, of course. This has a value and of course has to be covered. So what we see here is, of course, I've just made these question marks for grid augmentation costs, because this is nothing you can really calculate. This is project by project. It can be high, it can be quite easy. So whether grid augmentation is a better option than installing a VRDT or doing something else, of course, the network operator has to justify and explain to the AER how he's spending his money. But as, of course, what you can see here, also with the cost degrees that is happening with larger units, of course, tap changers are manufactured and produced not only for a single size of a transformer. So it's a product that is available and would fit in a range of power range of a distribution transformer. So with increasing costs and power range of a distribution transformer, also the costs of a tap changer are less significant. And that's why, of course, for bigger distribution transformers, this is finally not a big topic. Yeah? And these costs that I've mentioned here is also for volume 1. So not talking if there is a mass market already or if customers are buying higher volumes. So that was just a guess to give an overview about where we are. But I would appeal to everybody who's anytime trying to make a comparison should, of course, not just compare the regulated and the unregulated transformer costs. A fair comparison would only be comparing the investment with the grid augmentation costs that are needed in different cases. And of course, this might be also a good option in some cases as well, for sure. Yeah. So how about the VIDT rollout in Australia? So where do we stand? I think most of you have seen this assessing DR integration expenditure consultation paper from the AER that was published in November last year. And I have, in preparation of today's webinar, gone through a couple of feedback letters from different network operators in Australia that show they have notified the technology or the VIDT technology and are willing to invest and roll out the technology because they are convinced they can help them with ensuring connecting more and more solar roof installations to their networks. Evo Energy is one. Yeah, so the on-load tap changer here is actually mentioned in their response on that. We have others here as well. SA Power Networks has mentioned to replace tapless transformers with new transformers with OLTC. So a lot of interest or things are already happening. Yeah, so we are not only talking about trials anymore. Some network operators are rolling out the technology as well. Yeah, looking into Victoria, another example from City Power and PowerCore, who've done some trials and rolling out this. Also in a different use case as the standard use case, MV/LV regulation. So PowerCore has installed the technology in RevCal solutions that I will also talk a little bit more in detail in a few minutes. Yeah, so looking on some trials or projects here in Australia. Just to mention a few, some slides here. Essential Energy have been one of the first, I think, running this MV regulator here, 33 to 11 kVA, 2 MVA transformer, because also a high reverse power flow caused by renewables in that area. So not heard of any complaint. I think it's running smoothly after installation. And below is the second use case from Victoria. PowerCore, everybody who's not familiar with the RevCal solution, that's a rapid earth fault current limiter. And the tap changer there was integrated to regulate the voltage. If one of the three phases, of course, has touch ground and probably a fire is starting, then of course the voltages on the other two lines will be boosted to supply still enough electricity to the customers. So interesting technology on, I think, YouTube and LinkedIn. There are some more videos from PowerCore about this kind of application as well. So 22 kV, 3 and 6 MVA pad-mounted stations are going to be used in or installed already in Victoria. The Evo Energy use case, I think the ACT made it quite clear. If you look on some other publications, of course, there as well, I think they would like to let all customers install the highest amount of of solar into their networks. They have decided, okay, for all new or even some existing substations, we will install 750 kVA voltage regulated distribution transformers, regulating the LKV to supply good voltage within the plus minus 7.5% regulation bandwidth to customers in Canberra. Western Power, there's also a larger trial going on. Yeah, so I won't talk about this. Yeah, so our colleague Sherwin from Western Power is waiting to tell you a little bit more about this also in a couple of minutes. AusNet. AusNet is another interesting use case where we are supporting them with a 3 MVA unit. I think it's part of some substations, primary substations, where the auxiliary supply and the voltage stability has become an issue. So some bigger MV, LV applications there, and there you can see also they have gone to a 17 position tap changer. Yeah, just trying to regulate the voltage very smoothly to have no issues with their I think protection equipment in the substation and so on. And then another interesting use case I think we are running now for a couple of months, beginning of this year, a nice single phase swirl application of a pole mounted 25 kVA transformers, where I can also show you some pictures. So that's the first prototype. This was used, I think, for a fair only. So that's not the actually installed device. On the next slide, you will see some pictures of the installed device in South Australia. So now I can't see my slides anymore. So what has happened here?
You just lost your slides there, Thomas.
Okay. Yeah, sorry for that. I think my PowerPoint has dropped out. I'm just restarting the presentation and try to be there with you shortly.
No worries, thanks for that. And just a reminder, if anyone on the webinar does have questions related to what they've seen so far, or what they is yet to come, please do ask them in the chat, and we'll put them to yourself, Thomas, and or maybe Sherwin at the end.
Yeah, PowerPoint is restarting, so just a second, please. Can you still see my screen?
Yeah, I can see your screen, just no slides at the moment. Maybe while we're waiting for that to come up, okay. Thomas, just ask a quick question around uptake of this technology. How, in terms of globally, have you seen a real increase in it in those markets outside of Germany and Australia?
Yes, particularly in Europe, the technology is kicking off, or has kicked off already 2018, 2019. So I will show you some overview, I think, of the rollout that is happening in Europe already. So can you now see the slides again?
Yes, I got your presenter view. Yep.
Yeah. Okay.
Yeah, there we go.
So there we are again. Sorry for
Thanks,
for the short interruption. So that's the single phase unit installed, I think south of Adelaide there. Yeah, so just a small pole tranny, and yeah, the network operator SA Power Networks has also allowed me to share some results. So here you can see some results prior to the installation of the transformer and also after the installation. So just be aware the upper picture is just 10-minute aggregated readings, where the below one after the installation is 10-second aggregated readings. So it looks a little bit unsmooth there, but of course much higher resolution. Of course, the main task that the tap changers should solve, as you can see on the right on the results, of course now the voltage is within standards. Which wasn't the case before. So nearly 255, I think, volts they have seen during the day, which is of course out of the limit in South Australia. Regarding some settings, of course, they have not integrated the device into SCADA. So they have just a basic relay that we can do them some settings, play with some time delay. And the 10-second time delay they have found a little bit too fine. So they have modified this to 20 seconds, which was finally help them to see only 4 or 5 tappings during the day. So that's maybe another question that might come up later on. How many tappings do we see with a VRDT? It all depends, of course, on the setting of the device itself, and then of course you have to consider and find out what's the best setting, of course, for your network. Last but not least, there's another MV regulator installed in New Zealand with PowerCore, really long feeders, so they have a lot of I think weather outages there. It's not really this reverse power flow of renewable thing in New Zealand. It's mainly to ensure that if they have weather impacts and voltage increases due to disconnection of some assets, to still being able to supply accurate voltage to all of their customers along this 40 kilometers feeder there. So just some pictures of different units from the local OEMs. I'm showing all of them. So everybody in Australia has experience with building VRDTs with on-load tap changers and can deliver any product, I think, for any use case that we can think of. So coming back to Adrian's question, so what do we see right now happening in Europe? So there are a couple of I think network operators we are allowed to share that are pretty much away from trialing these units. This has been done in the last 10 years, and they have now decided to roll out their technology massively in their network, because they have done some studies, done a lot of simulations about what's happening, what's coming in the future regarding DR integration and also uptake of EVs, of course. And they're quite confident that the technology is working, and they can reduce their spendings in the network by using voltage regulated distribution transformers. Another interesting slide is this one. I will just try to touch this only quickly, because we would like to come to Sherwin as well and his slides. So that's an interesting overview of I think some different MV networks and the active and reactive power flow that you can see over the HV and MV transformer. So a typical load pattern is the red one that you can see see here, that's a primary substation with no reverse power flow at all. But you can also see that, controlling inverters and playing with reactive current also to integrate this in their voltage regulation scheme might change the picture, quite drastically, of reactive power flow. VRDTs have the ability, of course, to support reactive power correction if the network operator is trying to achieve that, of course, with controlling inverters, because it can solve the local voltage issues in the LV just by regulating the transformer. So both technologies can work hand in hand, and that's a quite, I think, interesting result. But also, of course, think about and take care, of course, about your usage of inverters in the future. As we all know, the spinning reserve and the synchronous generators will be disconnected coming up in the next, I think, 20, 30 years. So we will have an electricity system with much more power electronics and inverters. And then, of course, different technologies have to solve the same issues that we see today. Of course, voltage control, reactive power flow, and also, of course, frequency stability to keep the system alive and allow sufficient electricity flow to end customers. So the last presentation, I think, from my side before jumping over to Sherwin at Western Power is this one where the CEO of Avacon Grid has seen the technology and made the decision to invest in this technology quite massively. And if you look on the second statement that he gave, so they have really come to the conclusion, so why shall we buy unregulated transformers any longer? Because even if we now replace older distribution transformers, and as we know, DER integration will of course still continue, and also electric cars, like the one here in the background of this photo, will continue as well. So they have more or less decided just to install regulated distribution transformers from now onwards. So that's the end of a long rally and a lot of trials and a lot of network simulation. But that's actually happening in Europe now more and more often. Network operators jumping over and making use of the technology. But now coming back to Australia, so that's the, I think, perfect handover slide now to Sherwin, to give him some time now to share his slides and explain a little bit further about what's going on in WA. And of course, happy to answer some questions once, of course, we have ended our presentation.
Thanks, Thomas. I've just handed over to Sherwin. I can see your slides there. If you, yep,
right,
they're up there. All right, take it away, Sherwin. Thank you.
And you can see the full presentation there.
Yes, I can.
Yeah, great. Okay. Thanks, guys, and thanks, Thomas. I'll just probably give a West Australian perspective. We've been working with MR and our transformer manufacturers for a little while now, and we've got the same problems that everyone else has, so I won't dwell on them too much. You can see that duct curve changing over time at one of our substations, and pushing into reverse power in the middle of the day, and then hitting peak alarms in the evening is not uncommon at all. So as Thomas alluded to, in WA, unfortunately, we still have some very tight voltage regulations, a nominal of 240 and not 230, and a plus or minus 6. And that was from the Electricity Act of 1945, which we're trying to get changed, but that needs to go through Parliament, which makes it a little bit of a drawn-out process. But nonetheless, we're trying to work within those and push towards, the idea of the Australian standard, which is a much broader range, or a European standard. In preparation for that, we did some work with the University of Wollongong, where we asked them to test a whole bunch of equipment down to really low voltages, and what we found was that nearly all the equipment that we got them to test worked perfectly okay down to like 180 volts. So I guess we can see that probably Australia is a relatively small market, and manufacturers aren't going to produce something bespoke for us. They're going to produce it for a larger market, the European market, for example, and it'll just get sent here for the most part with the same operating tolerances. So by having a very, very tight range, we're actually spending money on the network unnecessarily when we could, let that range go wider. So we are trying to get that changed. So we started to see some real problems in 2017 and 18, where we had changed the settings of our zone substation AVRs and tried to reduce the voltage that way. Here's a capture of one of our substations. The top line shows the voltage control. The bottom blue is the tap position on those zone substation transformers. You can see over time they've tended to come down from the higher transformer tap positions, and by 17, 18 we hit the bottom tapped and struggling to achieve voltage control as they can't go any further down from a transmission supply side. So we had some quick short-term solutions. Give you some background as planning engineers. You always look at what you can do in terms of short, medium, and long-term solutions. So we did change the set point of those transformers, and that did give us some reprieve, but we ran out of taps very quickly. We were able to do some HV network switching and doing some feeder swaps on the same zones. You might have one feeder that's got a lot of reactive reverse power, and maybe if you change some open points and do some switching, you can fix that and hold the voltage up for a short period of time. And also changing the distribution transformer taps, but that's problematic because you might change them in summer for one condition, with air cons being on at night, and then in spring and autumn when there's beautiful sunny days and lots of solar and reverse power, you're going to have to send the crews out to change the transformer taps again, and so that's not really a position you want to be in long term at all. In terms of medium terms, we looked at some shunt reactors on the transmission systems to hold the voltages down where we could. More voltage regulators on our long rural lines, or distributed StatComs, and some feeder or conductor upgrades. That's to assist with impedance issues. But really what we wanted to do is get to some longer term set and forget type solutions. We're changing standards in our power transformers such that they have just as many or even more tap down positions as they do up. Historically, it was very rare to require tapping of the voltage up. The transformers required to tap the voltage up because of load drop on the network. But in recent times, we found that you also need to pull that voltage down because of reverse power flows from all the solar. So if you look at our historical standards and what's in the system now, it's non-symmetrical because no one ever thought of this issue years and years ago. We've been asking new settings for all residential solar to have volt var introduced. which means that they will that the residential solar will sink some reactive power to try to hold the volts down, and that will, you know, proliferate through as more and more customers connect to the new standard. We tried these voltage regulating distribution transformers that Thomas has talked about, and that was a part of our long-term certificate solutions. I'll go into those a bit further. The community power banks, they're basically batteries in the park, which customers with solar can access, and they will soak up the power during the day, and customers can utilize their own power in the evenings. And some controlling of DER projects and trials to see whether we or aggregators or retailers on our behalf can control the distributed energy resources to assist with this, usually for money, of course. In terms of this conversation, we've been trialing 11 distributed voltage controlling transformers. Now, Thomas talked about the method. You know, you typically have a medium voltage run, which might already be at the high or low end by the time it gets to your fixed tap transformer. And then if that problem continues, you get outside of your limits, dragging those voltages back in within prescribed limits with that voltage regulating distribution transformer means that your LV customers can be kept within those tighter bandwidths as required. So, you know, we did a trial, and we actually did it with transformers that already needed to be replaced. Now, the trial's taking place. Well, it started off last year, but we've just started installing the majority of them this year, 2020, and we'll be doing it for 12 months. So, you know, the proposed benefits are pretty obvious. You're going to be within the standard requirements of voltages. You'll be able to connect more solar or electric vehicles in the future, and keeping voltages from creeping up too high will actually increase the life of those apparatus. So that really helps customers out. The other thing that we had as a proposed benefit is we would decouple the residential PV inverter reactive power output from the street. And so therefore we could ask all the DERs to provide us with what we wanted in a controlled way, and that would be decoupled from the source voltage, which we could control separately. So that was an extra nice to have. So how did we pick these locations for the trials? First of all, we did a desktop analysis to see where we thought the problem was. Then we deployed data loggers to some of these candidate sites, one at the start of the LV feeder where the transformer is, and one at the end. And then we analyzed that data to make sure that the sites that we chose for the trial were appropriate. And from a larger pool, the way that we selected that was we wanted to use transformers that were currently either overutilized or were in poor condition and needed to be replaced anyway. So we said we need to change these transformers anyway, so why don't we change them with a tap changing transformer. We also wanted a pretty large voltage drop across the LV network, which we could test with simulation software, and also a high penetration of PV on those feeders relative to the size of the transformer. So the other thing we wanted to do is that we wanted to look for sites where the transformer was actually a fair distance from the zone substation, which meant that the voltage that was supplied to the transformer via the medium voltage was in itself, relatively problematic. And so, we wanted to see if we could, trial this in the worst case problem where you've got swinging medium voltage and LV issues as well. And we also wanted to do it where the LV conductor assets were in relatively good condition. We didn't want assets for the conductors to be in poor condition, because if those assets are in poor condition and you need to replace them, chances are you replace them with new conductor, which is a new standard, which is thicker conductor than the old days, and that inherently has lower impedance values. And usually when the when you fix it with those kind of conductors of lower impedance, the voltage problem also goes away. So that's an example of one in our test center. You can see it's a normal transformer. We have two normal distribution transformers supplied by our manufacturers, ETEL and Tyree. We asked them to just make one with tap changes in them and a control box. That's the wiring there that you can see on top that goes into the control box, together with a little mount on top where the motor drive unit sits. So that's a Tyree unit, very similar, just to show. So we went for a pretty wide wide tapping range. So 9 taps plus or minus 10%, 2.5 steps, and we standardized them through 315 kVA pole top units. The trial. The reason we did that is because we had some 100 kVA transformers that needed to be upgraded and some 200 kVAs that needed to be upgraded, and we just jumped straight over the 100 to 200 option and just did the one transformer straight to 315, which would make the whole thing a lot more streamlined and cheaper. So we also looked at using what MR calls a TAPCON dynamic set point control, or TDSC. This is effectively a real power droop function, and what that means is fundamentally, if you are pushing into really big amounts of forward real power, then that means you're going to have a voltage drop because of all the load, and the control system will push the voltage of the transformer up to allow for a voltage drop. And conversely to that, if you've got reverse power going to the transformer, you'll have a voltage rise from there, and hence what you want to do is drop the voltage of the transformer to a really lowest possible voltage to allow for a voltage rise along that feeder, and that's one of the methodologies that we used. So that's just one being constructed. You can see the pretty standard pole top transformer on top with a control cubicle where the guy with the ladder is, with the RTUs in there as well. So Western Power actually opted for the SCADA. So we've got it coming back to our control center, and we're also taking all the data into our historian databases. And this is some very preliminary results because we only recently installed these. So these are the loggers from the end of the feeder, and you can see under the before case we were getting some pretty high voltages, 254 volts, and in this control system, which is a fixed output, so we said no matter what happens on the supply side to the transformer on the MV, we just want you to keep the transformer voltage fixed at 243 volts. And so you see, even with that method, you can see that the after situation, we have a much better band of control, if you like, and voltages are hitting 248 max instead of 254. It is pretty good, but we are seeing some low voltage issues because WA has a very tight band, unfortunately. So then we turned on the TDSC function for a different site, and using the TDSC, you can see the before situation of voltages of 256 volts or thereabouts was brought into very nice control, not exceeding 250 volts, and with a much tighter under voltage in this instance. So we were able to keep the voltages within that kind of 230 volts. But this is obviously programmable, so from there we may choose to bring everything further down which is probably what we'll do. So we'll shift the whole voltage control scheme lower, which means that we should get better control. And when WA goes to the either the European or the rest of the Australian standard for voltage range, we can very simply just change our set points to bring the voltage down to those levels as well. Here's a screen capture from our control center, and this I just grabbed these today actually. So one of them I grabbed, the one on the left I grabbed at around lunchtime or midday, and it's kind of a mixed cloudy day here in WA today, but you can see we're bringing back all those voltages. In this instance, the kilowatts were reversed because of the solar, negative 22 kilowatts, and that's why the transformer was on tap 4, and the voltages were at around 230 volts supplied by the transformer. If you look at the one on the right, I took that in the late, well, not late afternoon, but just today, which is just before Thomas finished up, which is about 2 p.m. And with some cloud, and you can see the transformer is switched over into forward power. So from negative 22 in reverse to forward power 46, and you can see the transformer shifted to tap position 7 and supplying 245 volts, knowing that the voltage is going to be dropping from there. Yeah, that's pretty much it. So happy to take any questions.
Thanks,
or happy to go back, and I kind of blitzed through that pretty quickly because of time. But if anyone wants me to go back and look at something a bit further, we can do that too.
Appreciate that, Shervin. So a couple of questions have come through online. I can see Thomas has been very proactive about answering those. But maybe for everyone's benefit, Smolka, would you be able to take us through some of those questions and the response from Thomas? And Thomas, if you're able to then build on that if required.
Sure.
Yep, sure, no problem.
Great. So the first question we had from Simon was, why didn't Sappen integrate VRT with SCADA? Was it cost related? And a related question came through from Adrian about comms and whether it's required at all. Thomas, if you want to talk to that.
Might be muted, Thomas.
I don't know if we've lost Thomas or not, but I can certainly give Western Power's view.
Okay,
for us.
No, sorry, I couldn't hear half of the question. But Shervin, please go ahead.
Sure.
So just quickly from Western Power's perspective, for us, because it was a trial and we wanted to better understand all the different parameters, including whether or not we wanted to keep the same tap ranges for a final specification when we move forward. We thought that the SCADA data would be valuable for the analysis. We may, based on the SCADA data that we have, decide that we have got the standard right and the settings correct, and we don't need them moving forward. But for the purposes of the trial, we decided that we would like to have them. And yes, of course, they're more expensive.
Great. Thanks, Shervin. Thomas, did you want to add to that at all, or?
Sorry, I lost you when you were raising the question. What was it about?
It was related to communications and whether they're required for VRDTs and on the topic of SCADA as well.
Yeah, I tried to cover this in the chat already a bit. So it's not a must in general to operate VRDTs with running SCADA connection. Of course, you could remotely use them if you have SCADA and see these values that Shervin has shown in the control center. And of course, I mean, cost is also a kind of an issue. And for most customers that we have seen, is most start with, of course, a second relay that is able to communicate also to SCADA, so to have the unit visible, to know what it is doing and how it's going to be operated and everything. But once they have learned the lessons from some trials, and they're quite okay with having a nice transformer which they can, let's say, set and forget, that's usually the most preferred option for larger rollouts. So, I mean, it depends on customers' preference and, of course, of their internal use case and how they're going to use these data, of course. But I think definitely, finally, the cost is maybe the main trigger to decide whether this should be used if you invest largely in this technology or not.
Yeah, one of the other things for us was also a transition into getting better distribution visibility in general. We only just started our AMI journey, and we're relatively blind on our LV, and so these type of data points allow us to kind of better estimate what is happening on the LV, especially with solar.
Excellent, thank you. The next question we had was, Thomas or Shervin, if you could please mute yourselves. There's just a bit of feedback coming through. A question from Josh: is there a risk of influencing the MV voltage level if enough voltage regulating distribution transformer units are installed? And if they are, then is there a possibility of them causing nuisance tapping? And then is there also a risk in situations where LV networks may be paralleled or reconfigured? Open to both Thomas and Shervin.
Yeah, we have never heard any negative feedback if, of course, network operators are using the right settings, and of course thinking about this specifically. I mean, if you remember that, of course, tap changers are regulating power transformers on all voltage levels already for 100 years, and there might be, of course, also other transformers that could probably interact against each other, also on higher voltage levels. This so far has, I think, never been a real issue we are aware of. But of course, it's necessary to consider behavior, especially if you do some remote control of circuit breakers and come from an open loop to a closed circuit or whatever in different network configurations. This of course has to be considered, but it's definitely not a risk that people can face if they discuss and think about this seriously.
I'll just add the second part of that question around LV paralleling. Yes, we certainly had the question from our crews as well. Where we landed on is, at the moment, there's certainly no guarantee that the endpoints of any two LV networks that interconnect are going to be remotely close to each other in terms of voltage. You might have one network that's relatively long at the switching point, and another one that's relatively short from the transformer. You might have one that's got lots of solar on it, and the other one doesn't. And so what we've said to our operators is, if you can measure your voltage at the different ends, then you can use the tap changing transformer in manual mode in order to try to get the voltage at the endpoint as close as you can to enable you to close that in relatively safely, and that's how we've been going about it.
Great, thanks Thomas and Shervin. One last question from Kevin. Can the TDSC set points be set remotely?
That's a good question. I don't know. We're just starting to play around with it, so I don't know if Thomas has got.
He did respond.
Can you push that to the SCADA unit?
It was a yes from Thomas.
Oh, yes, from Thomas.
Yes, yeah.
Even better. Saves
Okay.
me going to go out on site when.
Yeah.
when
Please try that, Shervin, and let
abortion.
me know.
Yeah, hopefully it's not like some other firmware upgrades on other devices, but I'm sure it will be reliable on MR products.
All righty, thank you very much, Sanika. I think that is all the questions we had through the chat.
Yep.
Excellent. So just a very quick reminder, we do have our next webinar on the 18th of August, focusing on synchronous condensers. So looking forward to that one. And lastly, I just want to say a big thank you to Dr. Thomas Smolka and Shervin Fahmy for joining us today and giving us some insight into the VRDTs. If you would like to get in touch with either Thomas or Shervin, their email addresses are there on the slide. Likewise, if you want to get in touch with a representative from the NGN, you can contact us at that email address there. And Sanika, you had something you wanted to add around the A2 transformers?
Yes. So the A2 panel would like to, I guess, gather your burning questions around transformers. I guess if you think of any post this webinar, in the next few days, weeks or months, we want to start collating these and pose them to our very own expert panel within the CGRAE A2 committee. So this is just a quick note to say feel free to get in touch with me or to the NGN email address that's presented there on the slide, and I'll be sure to take down those questions, and we'll definitely get some responses around them through either a webinar format or other. Thank you.
Thanks, Sanika. So with that, I'll draw the webinar to a close. Thank you very much, Thomas and Shervin.
Cheers.